In this video, we're going to talk about weight and normal force. Let's start by seeing if we can solve this problem without actually knowing what weight is formally. A 0.5 kilogram basketball is in free fall. Find the net force acting on the basketball. Okay, well, so let's start with what it gives me. It tells me 0.5 kilograms, so I know that's the mass. And this net force thing, well, our net force equation, sigma F equals m times a, or mass times acceleration. I have the mass, but I don't really know what the acceleration is directly until I notice that this basketball is in free fall. And then I remember with Galileo that all objects in free fall experience the same acceleration due to gravity that we call 9.8, or it is 9.8 meters per second squared. So we use 9.8 meters per second squared. Okay, so now I can find the net force acting on the object. Half of 9.8 is 4.9. Kilogram times the meter per second squared is a Newton. Okay, cool. So yeah, I knew the mass of the object, and I know the effective gravity is an acceleration. So as long as it's in free fall, and that's the only thing that's going on, then I guess you could say that, well, gravity is the net force, and it's causing the acceleration of 9.8. So gravity is a force, and that's why its effect is acceleration. And you might notice that this is sort of the idea of the weight of an object. And that's because it is. Weight is gravity. In fact, the Latin word gravitas means heaviness or weight. And it is literally what Isaac Newton was talking about when he discussed the force of gravity as weight. So let's really get this down. Weight, gravity, this is a force. That is what it is at its core. And now you've seen that we can calculate how much force force of gravity there is by using the acceleration due to gravity. So sometimes we call this weight. We use a capital W. Sometimes we call this F. Little g for force of gravity. They're the same thing. But you can calculate either of them using the product of mass and then little g, the acceleration due to gravity. Now, here is a fun thing. 9.8 is a really annoying number because it's almost 10. So to help us out with all of our force problems going forward, we are going to say that g, the acceleration due to gravity, is really 10 meters per second squared instead of 9.8, and that'll make some of our mental math a little bit quicker. Let's do a problem with this. A 1,000 Newton rock is in free fall. Draw a free body diagram and then find the mass of the rock. Okay, well, remember, a free body diagram is just a dot representing the center of mass of the object, and we draw all of the forces that are acting on the object. If the rock is in free fall, then that means only gravity is affecting the object, and we can draw that force down. Now, you could call this force W. You could call this force Fg. But what I'm going to do is I'm just going to go ahead and call it mg, right? Because I know the force of gravity is mg, and it'll just sort of become a shorthand at some point. But you could always call it Fg if you want, force of gravity. Now, this 100 newtons, this is important because I know that that is the force of gravity or the weight of the object. So I'm going to write that down right away. Okay, if I want to find the mass of the rock, then what I need to do is take my equation, Fg equals mg, force of gravity, equals mass times acceleration due to gravity, and I'm going to need to get mass by itself. Now, to do that, I divide both sides by g, the acceleration due to gravity. And then I remember that g for us is going to be 10 meters per second squared to make these problems easier. So the mass is the force of gravity, 100 newtons, over 10 meters per second squared. Wow, that works out really well. Remember, a newton is a kilogram times the meter per second squared, so meters per second squared cancel out. And 100 kilograms over 10 is 10 kilograms. Boom. We just found the mass of the object in kilograms. Now, notice that the force of gravity, or the weight of the object, is different from the mass of the object. we typically confuse these things because in British units or English units, we use pounds for force. Pounds for force. We don't often use newtons to talk about weight. We talk about pounds of weight. And there actually is a British unit of mass. Do you know what it is? It's great. It's called a slug. That's right. The British unit of mass is a slug, British gravitational system. And it's about 32 pounds. That's how much force it has near the surface of the Earth. The slug. This thing is ridiculous. Okay, so anyway, we don't ever really talk about the slug here in America because it's pretty dumb. And basically, we're dumb because we don't differentiate between mass and force or weight like most other countries can or do. But we can be better. So pounds of force in British units, and then slugs for mass. Okay, now another way to understand the difference between the weight of an object as a force and its mass is to think about this exact same problem but on the moon where there is less gravity. So a 100 Newton rock is in free fall on the moon. Draw a free body diagram, find the mass of the rock. Well, so the free body diagram looks like basically the same. Mg for the weight of the object. And the force of gravity, oh, sorry, this problem is written wrong. This should say 10 kilogram rock is in free fall on the moon. Don't find the mass, but find the weight. Whew. Sorry, if you wrote that down, just change it. So a 10 kilogram rock, the same rock from before, is in free fall on the moon. And we want to draw a free body diagram and then find the weight of the rock. Great. So here's the free body diagram. The weight of the rock is the force of gravity. That's what we're trying to find. And remember that the force of gravity is going to be the mass times the acceleration due to gravity. So it doesn't say it in the problem, but I'll just tell you. On the gravity, the acceleration, on the moon, the acceleration due to gravity is about 1.6 meters per second squared. So if I take that 10 kilograms and multiply it by 1.6 meters per second squared, then I'm going to get 16 kilogram meters per second squared, or newtons. Okay, so a 10 kilogram mass on Earth is 100 newtons. On the moon is 16. Now, this aligns with our, kindergarten understanding of gravity. We know that there's less gravity on the moon. Well, until now, you haven't really known what that means. What that means is that the force, the pull of gravity, is weaker. It causes a smaller acceleration, and you would experience less weight if you were on the moon than on Earth, but you would not have a different mass. So the force is different, but the mass that you have is the same. Okay. So what happens if we have an object that's not freely falling and instead it's on some surface, like a table or the ground or whatever? Well, there's this force that we often call the normal force. And the normal force, normal is a word in math that means perpendicular. The normal force is a force of support. So you could call this a support force. Are there 2 P's in support or 3? I forget. So the normal force supports an object. If you have a table and say a box on top of that table, that box is going to have some weight force down, and it will also have support from the table holding it up. So we draw that force going up, and we call it the normal force. Now, there are different things that we can use. We can say F little n, but what I'm going to do is I'm actually going to call the normal force n, just so that we're writing less. And what you'll notice is that the normal force is perpendicular to the surface that is holding the object up, which is why we call it a normal force. Now, the normal force is often something that you have to find. Okay, so you normally that's funny. You normally have to find it. But if you were told that a bathroom scale reads a certain measure, well, bathroom scales or just scales in general, they measure the normal force. Because not force, normal force. They give you an idea, a direct measure of what the scale is supporting. So let's do a problem with this. You, 50 kilograms, I wish, are standing on a bathroom scale at rest. Draw a free body diagram of yourself. What would the bathroom scale read? Okay, well, let me draw a little picture of this first of all. Here's you. You're having a great time. Good job. And if I draw a free body diagram of you, which I'm going to pretend that you're just a little dot, and then your center of mass is represented by that dot, there's going to be a weight force down and a normal force from the bathroom scale supporting you up. Remember, it's normal because it's perpendicular to the scale, which goes left to right, so the support is up and down. Okay, well, here's the thing. If you're at rest, then that means that the net force acting on you is equal to what? 0. Remember, we call this equilibrium. If you're moving with a constant velocity or you're at rest, then all of the forces acting on you cancel or balance out. So that means that the normal force and the weight in this problem are equal to each other. Now, that's not always true, but in this problem, it is because you are balanced. Now, I could put little congruent marks on my free body diagram to remind myself of that fact. If I want to, that's great. But anyway, this is how I find what the bathroom scale would read. That is asking me to find the normal force. And now I just realized that the normal force is equal to the weight of the object. So all I have to do is take the mass, 50 kilograms, and multiply it by the acceleration due to gravity, which for this problem we're assuming is near the surface of the Earth, so 10 meters per second squared. So the normal force is 500 newtons. And again, remember that the weight is also 500 newtons. So in this case, the bathroom scale is telling you how much you weigh, because 500 newtons is how much support it's giving, and since it's at rest, you are being told how much you weigh. Now, bathroom scales don't always tell you, they don't always read your exact weight. If you've ever stepped on a bathroom scale, you'll notice that it sort of freaks out and needs a couple of seconds before it can get to the right number. And that's because the support that the bathroom scale gives you is different when you're not at rest. When you first jump on it, you're kind of like slowing down, and then you bounce a little bit. It's a whole thing. So let's talk about apparent weight and weightlessness. So basically, what we feel, our experience of weight, is not our actual weight force. It is instead the force that we feel holding us up. So what we feel as weight is the force holding us up. Like, think about where you are at right now and where you are experiencing something holding you up. Maybe it's your butt on your chair. Maybe it's your feet on the floor. Maybe you're laying down in bed and having a gratin watching this video. I don't know. In any case, the idea is that your apparent weight is a measure of the support from a surface to you, or the normal force. So the normal force is your apparent weight. Like on a roller coaster, at different points on the ride, the seat supports you more or less, and you will feel heavier or lighter depending on how much support that seat has to give you. Now, eventually you can get to a place where the normal force is not acting on you, and that's when you're in free fall. So when you're in free fall, then weightlessness is what we call that feeling when nothing holds you up. Like, when you're falling, there is still a force of gravity acting on you. So you still have weight, but you don't feel like you have weight because there's nothing pushing up on you. So your normal force is 0. All right, let's do a problem. You, 50 kilograms, still, I wish I was 50 kilograms, are standing on the bathroom scale in an elevator at rest. Okay, so the elevator's not moving. You step in the elevator, you're chilling, there's a bathroom scale, you're like, I'm curious, you step on it. The elevator wires are cut, and suddenly you and the elevator are freely falling towards certain doom. What is your acceleration? What would the bathroom scale read? Okay, so think about this for a second. If you're in the bathroom and suddenly the wires are cut, then that means there's no support from the floor anymore, and you are freely falling, which means the only force acting on you is your weight. Now, the acceleration is just going to be the acceleration due to gravity. That's it. And the normal force, it's not there because it's not pushing up on you. The bathroom scale wouldn't be supporting you anymore. That's why you're falling. So here you would say, oh, I'm weightless. I'm falling, so I would feel weightless, and that means the normal force is 0. Okay, let's change this up. You, 50 kilograms, are standing on a bathroom scale in an elevator at rest, okay? The elevator begins to accelerate up, and the bathroom scale reads 700 newtons. What is your acceleration? Okay, so here you are in the elevator. There's a bathroom scale on the floor. You're having a great time. Yay. Let's draw the free body diagram for you. We know that there is a weight force down, mg, and that is equal to, let's just write it here, 500 newtons, right? Because 50 kilograms times 10, 500 newtons. But now you're told that the normal force is 700 newtons. What does that mean? Well, what that means is the floor is pushing you up, and that's how an elevator gets you to go up. It first pushes you up a little bit to speed you up in the upward direction. So if I want to find your acceleration from this, then what I would do is I would say, okay, the net of these two forces. There's no x forces, they're all y forces, so we can just think the normal force is positive, so n, and the weight is down, so it would be negative, n minus mg. Okay? So that's how I find the net force, which is 700 newtons minus 500 newtons. That gives me 200 newtons, and it's a positive net force. I might draw that off to the side to remind myself there's a positive net force. Remember, never draw the net force on the free body diagram. That's a big no-no. Only the forces. Okay. Anyway, so the net force is 200 newtons. And now I know if I want to find the acceleration, then what I do is I remember, well, the net force is also equal to the mass times acceleration of the object. And I know that my mass is 50 kilograms. So if I divide both sides by m, I can find the acceleration. The acceleration is the net force, 200 newtons, divided by the mass of 50 kilograms. Remember, a newton is a kilogram times a meter per second squared. So 200 over 50 is 4 meters per second squared. Now notice that this isn't g. Okay, the acceleration does not equal g. 10 meters per second squared in this problem. And that's because I'm not freely falling. Instead, there is some force from the floor pushing me up, so I have to take that into account. That 700 newtons is going to reduce the overall acceleration that I'm feeling. But we were still able to use this as a measure of our weight, even though g is not an acceleration that we're experiencing. Okay, let's move on. You, 50 kilograms, are standing on a bathroom scale in an elevator at rest. The elevator begins to accelerate down at 2 meters per second squared. What would the bathroom scale read? Okay, so again, let's draw the free body diagram. Your weight force, 50 times 10, is still 500 newtons. But now we have a downward acceleration. So what that means is I know my net force is going to be down. And the normal force, which is what the bathroom scale would read, I know that it has to be less than 500 in order for me to have an acceleration that's down in the same direction of the weight. So I'm going to draw my normal force a little bit smaller than the weight. And again, I don't know what it is, so I can put a question mark next to it everywhere. Okay, so let's start with this. I know that the net force is equal to mass times acceleration. And I know that the acceleration is 2 meters per second squared down, so -2. And I can find the net force by taking 50 kilograms and multiplying it by -2 meters per second squared, which gives me -100. So I know the net force is 100 down. Okay, so if I already have 500 going down and I need -100 to go down, what would the normal force be? So here's where I think, all right, the net force is equal to N is up, so normal force is positive. mg is down, so minus mg because it's down, so negative. Well, I know the net force is -100 newtons. The normal force is what I want to find, and the weight is 500 newtons. So now do you see how much the normal force has to be? I add 500 newtons to both sides, and I get that the normal force is equal to 400 newtons. And that is what the bathroom scale would read. All right, let's try this problem. You are standing on a bathroom scale in an elevator moving up at a constant velocity. Okay, so the elevator, you're in the elevator, and you're moving at this point. That's you. Yay. What would the bathroom scale read? Well, let's draw the free body diagram. I know that you would have a weight force of 500 newtons. But what about the normal force? What would the bathroom scale read? Well, here's what's crazy. Constant velocity. Constant velocity, what does that mean? Well, that means the acceleration is 0 because the velocity is not changing, and therefore the forces are balanced. The net force is 0. So that means that the normal force acting up on you has to be equal to your weight in order to balance those forces while you're traveling. So we know that the normal force is 500 newtons. Now this is interesting. When you step in an elevator, it first has to push on you more than your weight to get you to speed up. But once you've sped up, you don't need as much force to maintain a constant velocity. So the elevator kind of pushes you kind of hard first when it starts, and then it eases up a little bit because it only has to support your weight as you're moving. Sort of crazy, but notice it the next time you're in an elevator. It's really cool. There's like a bump in the beginning. Okay, last one. You are standing on a bathroom scale in an elevator moving down with a velocity of 2 meters per second. The elevator begins to slow down with an acceleration of 2 meters per second. What would the bathroom scale read? All right, so here's the trick to this problem. We have to decide if the acceleration is positive or negative. You're told that you're moving down with a velocity of 2 meters per second. And then you slow down. What does that mean about the direction of your acceleration? Well, if you're moving down and you're slowing down, so like you're approaching the bottom floor, then that means the acceleration has to be up in order to be in the opposite direction. Remember, when you slow down, velocity and acceleration are in opposite directions. So this means that the net force is also going to point up. But basically, this 2, we have to recognize that that 2 is a positive 2 meters per second squared. That's the key to the problem. Okay, so let's start with the mass and the acceleration. Net force is mass times acceleration. Okay, so the net force is 50 kilograms times a positive 2 meters per second squared, or 100 newtons. And now I can draw a free body diagram and think about what's happening with the normal force. So let me do that to the side. I'll get rid of these. Okay, so free body diagram. The weight is down. The weight is 50 times 10, so 500 newtons. The normal force. I know the normal force has to be bigger because the acceleration and the net force are positive. So the normal force has to be bigger. Well, what is it? This is where we write our equation. Remember, the weight is negative and the normal force is positive because normal force points up, weight points down. And now I know the net force is 100 newtons. The normal force is what I want to find, and the weight is 500 newtons. So this tells me that the normal force is equal to 500 plus 100, or 600 newtons, because I add the 500 to both sides. Now, this would be your apparent weight. You actually weigh 500 newtons because that's the force of gravity pulling down. But in this moment, when you're slowing down, you're going to feel heavier, which when you come to a stop at the bottom of an elevator, you do feel heavier. And that's because the floor is supporting more than your weight. And that's the thing that we experience at our feet, and then it goes up through the rest of our body. Okay, so this video has been a discussion about the weight force, normal force, and apparent weight and weightlessness. Hopefully you had a great time, and you'll have the next video is going to be so much easier, and you're going to be so smart and wicked and awesome. Okay, thank you. You're done.